Neal Adams was born in Manhattan and is a successful comic book artist. He has produced highly acclaimed work for most, if not all, of the major comic book publishers. He cut his own path in the industry and has gone on to produce work based on characters he himself has created. He has worked in animation, creating book covers, theatrical costume and stage design, and even amusement park ride design. However, in parallel with this varied work, he has maintained a keen interest in the sciences. Quite a number of years ago he came across the work of Dr. Sam Warren-Carey, and he realised that the Earth hadn't always been the size it is now. In 2003 he started to post writings and artwork on his website regarding what he came to call the growing Earth. Over the next 3 years he went on to produce some very high quality digital animations which illustrated in a clear and compelling manner how the Earth has increased in size over millions of years. Here I discuss with him some of the evidence which proves that this growth has happened, and we discuss some of Neal's ideas and thoughts on how this has happened. Okay, I'm very honoured to be joined by Mr. Neal Adams, and we're going to talk about the growing Earth, or I've called it the expanding Earth. Neal doesn't particularly like that term. So
it's not a matter, just so we're clear.
Yep.
It has nothing to do with my liking or disliking.
Okay.
The term expanding Earth was coined first in the 1960s by Samuel Warren Carey, who wrote 2 books on the expanding Earth. Now we will note only briefly that Samuel Carey was a geologist. And being a geologist would never say a growing Earth, because a growing Earth implies a tremendous knowledge, 1, of physics, and 2, rejection of physics. So he wrote The Expanding Earth, and if you read his books or read any of the quotes from him, he will show you that he wasn't there to explain how the Earth got bigger. He was there to explain that the Earth got bigger. And so he used the word expanding because that's the best word he could use for Earth going from this size, say the size of Mars, to the size of Earth today. So something expanded or seemed to expand. Physics would tell you, no, that can't be there is no such thing as expanding in science. A rock doesn't expand. In fact, nothing expands, and one of the problems that we have with physics today is that the physicists are willing to use the expression on the universe, which is a total contradiction of everything that science believes in. And that's our problem.
All right, well, we'll come back to that and explore that in a little bit more detail, because that was sort of about 4th or 5th down my list, but that's fine. And so just a little bit of background then, Neal. I know that you've done your main area of work has been in comic art. Is that correct, or is that the wrong? Forgive me if that's completely the wrong term. Tell me what the right term is if that's completely wrong.
The right term is I studied art and I do comics.
Right.
I also design sets. I also do amusement park ride designs. I also do paintings. I also do illustration. I do many things as an artist.
Yes.
When I began my career, I know it's not the kind of word that we necessarily use today, but I was poor. I could not go to college. And I could not go to college, and I was something of a prodigy. I could also do art. And so I made the choice that I would earn a living out of high school. You cannot, as a scientist, earn a living out of high school. You can earn a living out of art if you're good enough. So fortunately, I was good enough, so I managed to earn a living. That did not mean that I did not continue my studies in science. I loved science from the time I was, 12 or 13 years old. I used to read science books as if I were reading comic books. And so anytime I get a chance to include science into the artwork that I do, I take that opportunity to do that, as well as spend my spare time, my copious spare time in studying science. I've studied all branches of science since I was 17, 16. Actually, as an enthusiast since I was 13, but 17 and 16 because I heard about this expanding Earth theory.
Okay, so that was really my next question. So when did you first come across the expanding, or you said the growing Earth? What, is that just in a book you picked up? How did you come onto that?
I was in the Museum of Natural History, and some guy was showing us through the exhibits, and he mentioned that there's this book on the expanding Earth theory, that the Earth got bigger. And I thought about it for a time, and I thought, what a stupid idea. And then I looked at maps of the Earth, and as an artist, I looked at the maps or the shapes of the continents, and I realized if I could make the Earth smaller, the continents would actually come together. There'd have to be a certain amount of jigging, but really not a lot. In fact, they would come together in a straight line. They wouldn't twist or turn or bend or whatever. They would essentially come together in a straight line. And so while I was studying this thing and picked up more information on the expanding Earth, I really went to the art. I went to the art of seeing how things move together, studying how if you put the wet sand on a towel at a beach and then you pull the towel away, you can see the break aparts of the various pieces, how some stay together and how some pull apart. So I studied that in all areas to understand this whole concept of what we learned at that time was the Pangea theory, which implied that all the continents on Earth made a Star Trek convention at one side of the Earth and joined in a big giant island, and then for some reason then broke apart. Why they would join and then break apart, I had no idea. I didn't understand the science behind it. And in fact, there is no science behind it. It's one of those like theories that is not based in science, but is based in isn't it a coincidence? And guess what? It's clear that continents pulled apart. Now we need the explanation, and now we go for the easiest explanation, something that doesn't offend all the other sciences. It was a big giant island. It doesn't matter that the outer sides of the island were break-off areas. They went slant right down into the ocean, just as the Atlantic Ocean does. Didn't matter that the age of the Pacific Ocean was the same age as the Atlantic Ocean. It didn't matter that the profile of the continents was exactly the same in the Atlantic as it is in the Pacific. Somehow, we being Western man, okay, we being American Europeans, came up with the theory. We didn't consult with China. We didn't consult with Australia and say, gee, don't you think this is a great idea? We just said, being Westerners, well, the Atlantic must have come together and all the continents came together there. A stupid, a very parochial concept to begin with. And as I studied, I thought, wow, if I was an Australian, I would have a totally different point of view. Why are you looking at the Atlantic instead of the Pacific? And that's what Jim Carrey did. Jim Carrey did not come from America or come from Europe. He came from Australia, New Zealand, in fact. And he said, no, the ages of the Pacific is the same as the ages of the Atlantic. The progressive ages across the Pacific are the same as the progressive ages of the Atlantic. How does that make any sense? We have to explain that. We have a responsibility as geologists to just come up with some flighty theory because it feels good at the time. We have to give the science. We have to be responsible. And he said, the only way it could happen is if the Earth grew or got bigger.
Yeah, and I think you made that point very well in the videos that you did. I think you started doing those videos back in 2005, was it, or 2006 that you started to get those? Yeah,
something like that. Actually, I did them incidentally because I was doing a book at the time. And I thought, well, you know what? Since I've done all these globes all my life, now I have the technology. Now I have the studio. I'm a self-financed scientist, in effect. I make enough money, and I have computer technicians that I can actually do things that other people can't do. I can take those same maps that everybody either draws or whatever, and I can actually animate them so that you can see exactly what happened And I took, for example, my daughter, who is a very meticulous person, and I made her my critic. And I said, look, if I do anything wrong here, Zia, you have to tell me I'm wrong. You have to say, this is you're flying in the face of logic. Don't do this, Dad. And I would go back and think of it, and I would stick to it like a religion. And we would only animate what made sense and what was logical and sensible. So if you look at those animations, it's really hard to find an error. I mean, there must be
I
errors,
think they're absolutely great, because I first came across those several years ago. I think maybe a year or two after you'd done them, and they're extremely powerful in helping people to see what's happened.
In fact, one of the greatest criticisms of those animations is that somehow I tricked them. They say, "You must have tricked me." And I would say, okay, well, let's look at both sides and see if there's anything that I did. I didn't trick you. Maybe I could have. It's possible if I had made that my goal, but I did not. And I had done these maps in the past, cutting out tracing paper and put them on small basketballs and all. It's so clear, and it's not just me. Okay, James Maxlow did the same thing. There's a German that did the same thing.
Klaus Vogel, I think his name, isn't it? Yeah.
And you'll see and the same continents fit in the same way. And we did it all independently. I didn't look at anybody else's work. Believe me, trust me here. I didn't look at anybody's work, and we all do it exactly the same way. Because as we look at the ages of the undersea are like a map that takes you back in time to bring these things together. There's no trickery. It's all there. The trickery is in the Pangea theory. There's so many things wrong with the Pangea theory that it boggles the mind. One thing, for example, is any geologist would tell you that the whole concept of the Pangea theory is that dinosaur, and this is part of what they came up with, dinosaurs could travel to, in a sense, all 7 continents of the Earth at many particular times in the ages of the dinosaurs. And that's part of the basis. Also true with plants and other animals. Well, the truth is that they will tell you with the other mouth, it will tell you that two-thirds of the continental plate 200 million years ago was covered by shallow seas. Shallow seas. That means that 2/3 of Pangea was shallow seas. It went right up the middle of North America. It filled Brazil. It filled all these areas. And in a sense, if you were to take a map of Pangea and you were to take a magic marker and fill in 2/3, any 2/3 that you wanted to with a magic marker, you would have what would look like the Philippine Islands. Now that would make of Pangea islands. Islands. They're not. It's not one island. There's no way that it could be one island because it was lower than sea level is now by 600 to 800 feet. So there's no way the dinosaurs could get to other areas of Pangea, even if Pangea existed. Beyond that, and even worse, geologists tell us Earth for billions of years. Well, if I'm in North America 200 million years ago, and if there were the Rocky Mountains and the Appalachian Mountains, dinosaurs couldn't get from the East Coast to Middle America, couldn't get from Middle America to the West Coast, because we had 2 mountain ranges in between. And in the middle was a shallow sea 800 feet deep. There was no way that this theory of the migration of all these dinosaurs could be true and the other be true.
That's mutually exclusive.
They're mutually contradictory. So everything, as I say, everything about the Pangea theory, is wrong scientifically. And all you have to do is study the different sciences to realize, oh, well, if I follow the migrations of animals, this doesn't work. If I follow the sea level, this doesn't work. If I follow the geology, this doesn't work. There's nothing about the Pangea theory that works. If you believe there were mountain ranges 2 billion years ago, guess what? There couldn't be dinosaurs, and they couldn't have migrated to where they migrated.
That's right. When you start to look at some of these basic things, I totally agree with you. that it doesn't stack up. It cannot stack up, and
But what I'm saying is, the more you study in the more sciences, the worse it gets. I'll give you one more example, if I may, before you go on. There are no fish. There are no deep sea fish, okay, in the deep oceans of any ocean on the earth. No fish fossil found older than 70 million years old. No fish fossil. Now remember, we said that the continent started to break up 200 million years ago. There is no fish fossil, and 70 million years ago is just like 10 million years before the dinosaurs were extinct, okay? There were no fish fossils in the deep oceans older than 70 million years old. Yet, we have fish fossils in our museums that are 400 million years old, 300 million years old, 250. We have it through the last 400 million, but none of them, not one fish fossil anywhere on this planet, was found in the deep ocean. Didn't exist. Because, logically, you would say they didn't evolve to live in the deep oceans until 70 million years ago. Otherwise, what is the answer? No, there is no other answer. You can, and believe me, I've spoken about this for the last 6 years. There is no answer that covers this. And if you find a scientist who would be willing to argue with me that there were fish fossils in the deep oceans that were 150 million years old, I would love to look at that proof. And I've had that out there on my site for the last 6 years, and nobody has successfully contradicted it.
That's interesting. That's certainly something I wasn't aware of, and I think that you get to the point where you have all these different types of evidence which show what's happened, and yet people don't want to know. They won't say you're wrong, but
no, say you're wrong.
Exactly. They don't say you're right either, which is the problem.
But that's why I believe in stacking up the facts. People talk about theories. I don't believe in theories. I think theories, a good way to go the wrong way is to accumulate theories. I believe in facts. And so when you talk to me, you'll find I'm going to give you facts. So why don't we just
Absolutely. So yeah, we've talked a little bit about the growing Earth and the expanding Earth, which you started off in the introduction. But I wanted to make that distinction a bit clearer for anybody that's not quite clear about that, because I know that I've made this video, which we might mention a little bit later on, and you didn't think that was right, which is fine, and so I wanted to try and just sort of give a clearer understanding of how you would differentiate between the idea of a growing Earth and an expanding Earth, and why you think that's why that's important.
Right. A balloon expands, okay? A balloon expands because you put air into it, okay? And the balloon doesn't actually get bigger, it expands, okay? An explosion expands, okay? Because you've thermally ignited certain materials that have the ability to expand, so it expands, okay? Nothing in science, unless you add another form of energy, thermal or chemical, or it really comes out to thermal, expands. There is no such thing, okay? One can use the word something seems to expand, or, Joey got fat, so he expanded, but he didn't really expand. He added more calories, added more cells to his body, and got
right.
Bigger. Okay.
So what you're saying then is that growing really means, correct me if I'm wrong here, I think what you're saying is that growing means more material is being added, but, right,
exactly.
And the expansion is where the existing material just moves itself somehow further apart or becomes, less dense, basically. Am I correct in that?
And that, by the way, is an impossible scientific concept. There is no such concept in science. It's like one of those science fiction things. You can say if such and such expands. It doesn't expand. Mr. Fantastic expands. No, he doesn't. He must be a balloon because he can't get that big. It's a scientific impossibility. We don't use it in science. We don't use it in physics because it doesn't exist. except when the scientists talk about the universe, and there they have a problem. And they have the problem because they see it seem to expand. And so they say whatever the universe is made of is expanding, okay? They will say that ad nauseum, even though they actually haven't analyzed or proved anything except that the universe seems to be moving outward.
Okay.
And so what happened was when Hubble discovered that the universe was moving outward, clearly it is moving outward, they said, well, it must be expanding. So they would use the analogy, explosion. That's
yes.
how they first, remember at the beginning they said, well, it's a big bang. It's a big bang. I don't know how you can interpret big bang as not an explosion. Excuse me, you guys may want to run away from it's not an explosion as fast as you can, Mr. Physicist, but I'm sorry, you called it the Big Bang, not me, okay? It's a bang. It's an explosion. Well, obviously wrong, because if it's an explosion, it must slow down, and it's not. It's speeding up. Wrong, okay? You can't use that. Oh, and now we're going to retreat from explosion, and we're going to call it expansion. The time-space continuum is expanding. Oh, gee, that sounds like, I don't know, Star Trek. Excuse me? Because you say so? I'm sorry. That's not how science works.
Okay.
Science doesn't work if your example doesn't work, you must find another example. What does Sherlock Holmes say? If you eliminate all the possibilities and you're left with one possibility, no matter how ridiculous it may seem to be, that's got to be it.
Right.
Okay. It's clearly not expanding. There's only one thing left for it to do, and that's to grow.
Okay. So we are then saying that more material is being added from somewhere to make the Earth and the other planets that you've talked about grow. Is that have I got that right?
Let's take the other point of view. We can look at that and say, okay,
all right,
yes, let's be added. How did we get the universe in the first place?
Okay. Yep.
I mean, did it explode into existence? Haven't we put that aside?
Sure. So you're asking the question then, where did the material that makes up the current universe come from? Is that, am I interpreting you right?
Much deeper than that.
Okay.
It's much deeper than that, because that's where we get into physics. Okay. The physics is actually more interesting. Can matter be made? I would ask you that question. Can matter be made?
Obviously it can, because we are here, but...
No, listen. The problem is that you ask a geologist, okay, can matter be made? Of course it can't be made, okay? But in physics, matter can be made.
Okay, right, I see your point now, yes, okay.
Every electron on every atom in the whole of the universe was made by a process that we know. It's called pair production. A high energy photon flying through, coming in from outer space or flying around or manufactured in a lightning bolt or whatever, strikes nothing that we know of.
Yep.
Nothing that science knows of. Nothing that science knows of. Because no scientist will tell you what it hit, okay?
Right.
And that high energy photon, which is energy, not matter, splits in half and gains 1/2 electromagnetic field over here, and this side gains 1/2 electromagnetic field here, and this is an electron, and this is a positron. Both of them are matter. Now, if all you have in the universe, relative to knowledge, okay, is that the only form of matter that can actually be made by a process that we know and recognize and we can see every single day, anywhere, happens, we have to focus on that and say, if matter can be made, and this is an electron, remember electron goes around all atoms, and that's how it's made. We have to study this phenomenon enough to know how this process can lead to a matter universe, because we have no other process.
Okay, right. So the key underlying thing that you're presenting there is pair production, yeah? That this process of pair production is what is underlying this production in matter. Is that, have I understood you properly, or?
The creation of the matter universe begins with pair production.
Right.
But
Okay.
say this, and you know what? You can say this. You don't even have to say that. You can say, okay, the creation of 1/3 of the universe's matter, we know how it's made.
Okay.
Now, if you're going to say, if anybody's going to say an argument to me, well, what about the other 2/3? So I would then have to say, so you're admitting that pair production makes 1/3 of the universe, but you're not willing to admit that pair production makes the other 2/3.
So
I can go along and say, well, I figured out how to make 1/3 of the universe. You guys figure out how to make the other 2/3. It's a silly argument.
So you brought in the figure of 1/3 there. I don't. Could you clarify that? Because I haven't quite followed where that figure of 1/3 of the mass of the universe has come from.
Okay. Every electron in every atom of the universe. Okay. In every atom of the universe, you have exactly the same number of protons as you have electrons.
Yes.
You have the same number of neutrons as you have electrons. So there.
Except in certain isotopes, so they say that there's different numbers of neutrons and protons. But yeah, okay. But by the law of averages, go on. Essentially, okay. And you have free electrons. I mean, you can go through the details of, it's like how many colors are there? Well, there's 3 colors. So you can break it down into all the colors. But that means that 1/3 of the particles of our universe is protons. 1/3 of the particles in our universe is neutrons, except in the case of hydrogen. And 1/3 of the particles in our universe are electrons. Okay.
Now we have an interesting question. What happened to the positrons?
Antimatter.
Antimatter. We call it antimatter. Isn't that interesting how you can call somebody, there's a character in the Green Lantern Corps called Sinestro.
Yes.
He's a bad guy. How do we know he's a bad guy? Because we called him Sinestro. Okay? How do we think that a positron, okay, is antimatter? Because we called it that. Because when a positron meets an electron, they seem to annihilate each other. Wait a second. Oops. Stop science. Nothing annihilates. Nothing destroys. Nothing creates. Why did we use a word like annihilate? Because we wanted another Sinestro. I don't know why we did it. Science can be stupid, okay? So let's remove antimatter and let's remove the word annihilate and say the opposite particle from an electron. It's the opposite particle.
Okay.
Or, as some physicists would say, in a positron universe, the electron is the antimatter. See?
Okay, yeah.
So you have now the other particle, and when they join, they simply reunite. To be struck again by a high energy photon. Because what happens is when they come back together again, they seem to join. The energy that made them initially leaves in 2 particles, gamma ray particles, okay?
Yes.
Like light particles, boom, like that.
Okay.
And they disappear. But you see, they were disappeared at the beginning. Nobody knows what that high energy photon hit. Seems to have been disappeared. So simply it disappears. Well, wait a second. If pair production can happen any place in the universe, in your room, right next to you, okay, if it can happen any place in the universe, doesn't it mean that these things that make it are everywhere?
And so what you've presented there, I've thought of an idea of describing it. You've talked about pair production, I've heard of that before. The antimatter-matter interaction could be called pair destruction, couldn't it?
No, it'd be called joining.
Or pair joining, or pair joining. In other words, it is pair destruction.
Pair rejoining.
Because I see what you're saying. It's basically the opposite, though. That's the concept I'm trying to get to.
No, because the opposite is not the opposite. Okay. The positron has one positive electromagnetic charge.
Yes.
The electron has one negative electromagnetic charge.
Okay.
When they join, they become neutral.
Yes.
An electromagnetic field that you can't identify because it's neutral.
Yes.
Okay. So
So, but are you, can I just, however you describe it then, just to check I've got your concept right here.
Oh, you haven't.
Right, but let me try and just go back a step. Would you consider that, we've talked about pair production and the interaction of a positron and an electron, would you consider that's a process which is complementary to pair production, or is it just a totally separate thing, or is it like the balancing?
It's the opposite.
Would you regard it as kind of a balance for pair production, if you see what I mean?
This way. Think of it this way. You have a little electromagnetic field that's balanced, negative and positive.
Mm-hmm.
Okay. I'm going to give you an image, okay, that manufactures this field. Okay. The field is manufactured by, we'll say, just theoretically, because I really don't talk theoretically about much, and I mentioned before. I'm just going to give you an idea.
Okay.
We'll call it spin. Okay. The universe is spinning. In this spinning, the universe is pulling outward. Okay. In its pulling outward, it has nothing. It's basically nothing. We don't know what nothing is. We have no idea. And so pulling outward, it makes less than nothing. It makes a little pulling outward. Now that pulling outward is distributed through the whole universe by particles the size that Planck would say is the size of a particle. Can't get any bigger than this. Okay. And what it is a field. Suddenly you pull it apart, and then you have like a bubble. Call it a bubble. And then you have a point in the middle. The point would be the positron. It's the part of the field that wants to pull it together. Then you have the bubble, which is the part of the field that's being pulled out by the spinning universe. Okay? It just wants to get back together again, but the universe is pulling it outward. So now you have a bubble. Okay? And inside the bubble you have a point particle. Neither of them have a dimension. Just like a bubble in the water doesn't have dimension. The water ends, the air begins. So it has no dimension, okay? A point particle has no dimension as well. But it does exist as the bubble exists. Now, if a high energy photon, now it's a field.
All right.
It's a field because we've labeled it a field. This is the pulling out. This is the pulling back together again, okay? We send a high-energy photon, and we pierce the bubble and hit the point particle in the middle and knock the point particle out. Now that point particle goes out, and you have a out-facing field. In other words, originally you had an in-facing field where the field just goes from the bubble to the point particle in the middle. You knock that point particle out, and now the field expands outward. Negative, positive. Okay? Negative and positive. This is a half of the field. This is the other half of the field. This is the negative half. This is the positive half. Now they exist separate from one another, and they will go on to infinity unless they slow down. That field will expand outward. That field, each one of those fields will latch onto another field if it can. That's a stronger field that it goes by. So this is a half a field. Mm-hmm. This is the other half. This is a positive half of the field. Now, 1/3 of the matter of our universe is made of 1/2 fields. Not a whole field. 1/2 of a field. The positron is the same way. If you can preserve that positron, if you can imagine a circumstance in which that positron can be preserved, it doesn't have to destroy an electron. And that's one of the things that science hasn't done. They haven't preserved the positron. They're starting to do it in these colliders to preserve positrons. They're using positrons as a form of energy, just like you use electrons. Okay, but the electrons are safe. So now you've got multiple questions. Why are there so many electrons and so many positrons? And so few positrons, hardly any positrons. Where are the positrons hiding? Okay. What if I said to you, inside every proton, at the very center of every proton, is a positron?
Could be.
If that were the case, and if the positron is actually, if the proton is actually made of these fields, not of quarks, which is kind of a weird thing. But let's say it's made of these fields. Okay. Then every electron in our universe, mathematically, would have an equal number of positrons in the universe continuing to exist.
Yeah.
So the question is, what process would cause this to happen? And why haven't we investigated that process? We haven't investigated that process because we put fake names on things and we're not willing to study.
Well, I certainly say, we've gone into a lot of sort of detail there about subatomic physics, and I've certainly looked into that. You know, I sort of followed some of the experiments that were going on 20, 30 years ago, and it seemed to me that they were really trying to write the theory and then perform the experiments and say, oh yes, the theory was right all along. They didn't really seem to be, you know, I don't know, anyway, it just seemed to be a self-proving thing that they were doing, and circular arguments and things like that.
Let me tell you a story and see whether or not you see the sense of what you're saying within the story. Science studied particle physics until they got down to the electron, the proton, and the neutron. Okay, that seemed to be where they were going, and now the next process that they would continue to go to is to find a universe that had particles where there were 2 particles rather than 3, because now they had 3, electron, proton, and neutron.
Yep.
And then after that, to find 1 particle, okay, and then to find 0. That's the goal of science at that time. Suddenly, science discovered new particles.
Yes.
They thought they just taus and different particles. And so they became enamored of, oh, I found another particle. Oh, I found another particle. I would say, looking at the story from a little bit of a distance, I would say, well, wait a second. What if all those particles were made of those first bunch of particles? What if you deserted the cause, and the cause was to get from 3 to 2 to 1 to 0, okay, because you were entranced by shiny stones? What if those shiny stones were the same shiny stones? In other words, what if protons were made of these, what I call prime matter particles, these little fields, negative and positive? What if they were made of that? How would you know? You call it quarks because you think you study the outside of it. But in the same way, I would insist a snowball is not a snowflake. You can call it a snowball, but I say it's made of many snowflakes.
Yes.
And a snowball is not a snowflake. All it is a clumped together bunch of things that you have now decided to investigate as a clump without having taken it all apart and investigating all the parts. And you've called this clump quarks, and you call them 3 quarks. I would say to you, Mr. Physicist, where do they come from? I mean, we know pair production. We understand electrons and positrons. We have a pretty good idea. Where do quarks come from? They can't exist by themselves. They can't exist until they're clumped together. And if they're broken apart, they cease to exist again, just like pairs. So what makes you think that they are anything? Do they come from quarkland? Are they magical things? Do they only exist at the beginning of the universe? I mean, it does cut off an awful lot of research and thought, doesn't it?
It does. And it's
kind of things that, and there's 3 kinds. I'm sorry,
Yeah.
There's 3 kinds of quarks. And you start to contemplate this. You say, well, what if it was all just a bunch of little particles, and what you're measuring is the clumped together energy, just like you measure electron shells around an atom. Each shell has a different, each electron in each shell has a different energy level than the next shell.
That's
well,
right.
Wouldn't it stand to reason that inside a proton, if it's made of many particles, there might be a 3-part differentiation that
there
you could
could be. Yeah, I think.
If that is the case, why don't we continue the investigation? Stop closing the doors and look at the only particles that we know that can actually be made, and we can observe it. Quarks can't be made.
That's right. What they'll claim is, they claim that these particles are created in these high energy experiments, and they don't they don't see the particles themselves, but they predict the effects that these particles would create, and then they see those effects, and therefore those particles... I mean, to me it seems like they invent this particle, like this W boson. It was the W boson 20 years ago. More recently it's been the Higgs boson. And then they say they found it, and they seem to find every particle they invent.
Oh, I know. I find it to be ridiculous. And see, the thing is that I don't believe these theories. And the problem is that I have is that when I start separating things from facts into theories, I find a very, very small number of facts and a very, very large number of theories. And I notice that the characteristic of theories is every few years they get shot down. Facts seem to stay for very, very long times. And theories get shot down. It's, with the water at the center of the earth. No, you can't have water at the center. No, that's a theory. You have this. You have the Pangea theory. It's a theory, guys.
We'll get onto that later, because I'd certainly agree with you about the idea of theories and facts and how a number of theories are, put to one side because they're not supported by the facts.
Fact is pair production, and that's a fact.
Right. Okay? I mean, anything that you can do experiments on and measure, then you can establish truth from that.
Funny about that, isn't it?
Yeah. Anyway, we've gone off into quite a long diversion into particle physics and subatomic physics.
But you see, that's also the problem. The problem is that I did not enter this whole thing with thought in mind of just proving, and it was at the beginning that Carey was right. I entered into it to if I could, give the mechanism that the Earth could grow. In other words, I know as an artist and as a creative person that clearly it grew. I know from everything else, from the dinosaurs, from all the gravity, everything else, everything shows that it grew. So all I wanted to do was to give the mechanism, and that's what I began to study. That's what drove me into all the other stuff. Is that you can't find it in physics. You can't find it in geology. I'm sorry. You can't find it in geology. It's not there. You have to find it in physics. And when you go into physics, you have to cosmology. You have to go into all these other things and bring them in and then kind of smush them together and find out what science justifies what thing. Anyway, go ahead.
I appreciate that now more than I did before I had this conversation. So that's good. I think the next question. You've talked a little bit about Warren Carey, and you've explained, and I think, from what you've explained, you'd say the same about James Maxwell. It would be on the evidence that the Earth has grown, and you can see that, we've covered that very well in the initial discussion, I think.
You see, that's the thing I love about Maxwell, is that he's carried on the work of Sam Carey. Okay. Yes. And that's the great thing, is that he's done that, continued that work.
Right.
But again, he is a geologist, okay, and he can only do the geology. He cannot come up with the mechanism. He can try, but he'd have to reconvert his life. Okay?
Well, he's done that. I mean, to be fair to James Maxwell, Neil, he has he did this talk in 2005. I mean, I don't know if you watched that, but he does try, I think I watched that talk, and I have to say that the mechanism that he came up with, it didn't really to me, it just seemed like a hodgepodge of things, and it didn't really stack up to me. But he did at least attempt to do some explanation. I don't think he's perhaps.
So did Carey.
Okay.
Carey
yes,
tried
he did.
The same thing. He tried to do the same thing. But remember this. On the physics, I thought it would take me 3 years. It took me over 30 years.
Wow.
Because you have to spend a ton of time eliminating to get down to the bare bones of what the facts are. And I would say, if somebody said to me, why would it take you 30 years? I would say, because I'm stupid. I don't know how to get to the point well enough and intellectually enough to do it without just working at it like a dog to dig all this other crap out and throw it away to finally get down to what the final last little pieces are that you can build back up again. And what I find in science is that because we have all these theories, there's so many theories and so many concepts, but the answer has to be one, and it has to be simple. I go to art very, very briefly. Okay, how many colors are there? There are 3 colors, red, yellow, and blue. Of those colors, either greater or more or mixes of those colors, you make all the other colors, which comes out to millions. The same thing is true with light. Light is white, okay? And you can break it down into its various components, and you get millions of colors. So to get down to that white light, to get down to that red, yellow, and blue, very, very hard to get that crap out of the way. But that's the job. And that's what I did, and that's what I've come up with at the end, is to take all those very nice thoughts that people have. Oh, I've just been thinking about this for the last couple of months. No, that's not going to happen. It doesn't happen that way. Really, 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 it doesn't. 30 years. And I consider myself a relatively smart person. Clearly I'm not, but I really had to work to get to that, to see what the basic pieces are. The basic pieces are simple. And science has made them complicated. We are in a kind of weird dark age of science, okay, where technology is taking the place of science, and it makes us think that we're advancing, but we're not. We're using the same stuff that we used 30 years ago.
You might enjoy reading an essay that a friend of mine wrote, who's sadly no longer with us. It's on my website, by Lloyd Pine. He's written this essay called Why So Much in Science is Wrong. And I think that touches on, some of the things you were saying there. And I think, one of the issues, without going off too much on a tangent, is that science, mainstream science, tends to force you to work in a number of ways. And as you said earlier, it's very much harder to kind of take different branches of science and, and use them together to develop an understanding.
They don't speak the same language.
No, they don't.
Branches of science has their own language. When you speak to me, I speak street English. Okay, street English. I'm not using any big words. Positron and electron are very common words, and because they represent what you have on atoms. But that would be the most complicated. I don't talk in those because, in fact, when I talk to scientists, I stop them within a sentence and I say, no, you have to explain what that word means. You have to explain what that word means. I see geologists talk to physicists. Within 2 sentences, they don't understand one another. Yeah. They have no idea what they're talking about.
There isn't really a free and easy communication between the different branches of science. I definitely agree with you on that.
Falling into this dark age.
Yeah, and I think there is this because you're constrained to work in a certain way. And if you want to get anything published, if I wanted to get anything published, for example, in a scientific journal, I wouldn't be able to. There'd be no way I could get it published.
No, I know. I understand 100%.
Yeah.
I find myself in a very fortunate position. I am independent of all of these things, which could lead to disaster. And that's an easy thing to say. I have avoided as many disasters as possible, and I have retained my independence. I'm not writing scientific papers or any of that stuff. I don't have any theories about things. I just talk about the facts.
One of the things we touched on just briefly was, the thing that really, in the growing Earth, expanding Earth situation was the dinosaurs. And I realized, or I came across Stephen Hurl's research about the dinosaurs and how, we look at the land dinosaurs like the Brontosaurus, and in more recent times I came across a page which talked about the Brontosaurus's heart and how big it would have had to have been to pump the blood up to its head. Now, so the basic problem seems to have been that if we take the mechanics of the dinosaur's body, which you can make calculations on, and Stephen Hurl has done this in his book, Dinosaurs and the Expanding Earth. He calls it expanding. Obviously, we'll probably use that word again, but I think we've made the distinction clear.
I'll slap it out of him.
So, can you talk to me about the dinosaurs and what your thoughts are on that, Neil, please?
Well, I don't hardly have any thoughts. I mean, the problem is that it's if you have a 60-ton sauropod, it couldn't possibly walk around in this gravity. There's two scientists that have a special on Discovery or one of those channels where they argue about Tyrannosaurus Rex and that he's so big that he can't go faster than 10 or 12 miles an hour, and then they get angry at one another. The other guy says, no, it ran very fast. They get angry at one another and they yell at one another and they act like it's a big issue. And obviously the issue can be easily solved by quartering the gravity and saying that a T-Rex would, weigh maybe, 2 tons, 2.5 tons. And that's pretty much it, and it would work. The physics of it, it really comes down to this. A thing can't get longer and higher without getting wider. That's how the physics works. So if you could take an animal and make him as big as a T-Rex and make him as tall as a T-Rex and as long as a T-Rex, but not as wide as a T-Rex, it would work. But no, unfortunately, you can't. You have to make them as wide as an elephant. So when you do that, the physics stop working. Well, I've studied anatomy as an artist. Okay?
Yes.
Because, as I say, I study many things. Okay, so in my study of anatomy, we have certain muscles and certain tendons. Okay, if you have a tiger's back leg, okay, pretty similar to a T-Rex's back leg, but of course, T-Rex started first. But that tendon that goes off the top of the back leg is, maybe 1.5 inches big, and it grabs the back of the bone that goes down to the foot, and then it goes up into the thigh and impacts into the upper thigh bone. That tendon on a run in this gravity would snap like that. Okay. If a T-Rex running, even walking, snapped his head around to look from forward to a left angle, his head would fall off. It's like imagining a device that had a motorcycle. You put a motorcycle at the top of it and you whip it around. That motorcycle would keep on going because it's too big, okay, in this gravity. If you measure the stride of a human being at a run, a stride of a human being is maybe 1.5 feet, regular walk. At a run, they can go between 3 and 5 feet, okay? A T-Rex's walking stride is 12 feet. Try to imagine a run, okay, that is less than 25 feet. One step, less than 20, can't be. It's bigger than 25 feet, okay? If you had any kind of gravity, what happens when you take a stride when you're running is, and the reason the math works is that if you were to try to take that length of stride and you took as long as you took a step, you'd fall down because you get to your next step to keep you running. So if you took like one running step and then tried to stop, you'd fall down. You have to one step after the other. So each step has to be a certain length of time. So if you take a T-Rex and you make his stride 25 feet, okay, and it's probably more like 30, and then you make it take the amount of time that you take a running step, okay, he has to run 75 miles an hour. 75 miles an hour after creatures that look very much like him, which also run at 75 or more miles an hour, the way antelope run away from lions, okay, because that's the relation. 75 miles an hour for a T-Rex, according to the scientists, would be impossible.
Right.
That would be impossible. An elephant can walk. I mean, you may not know this about elephants. Elephants do not run. In other words, to run, you bend your legs.
Okay.
To run. Okay. An elephant's legs are locked together, and he walks like tent pegs. It's like tent pegs walking.
Right.
He doesn't bend his leg to walk, because if he did, it would snap. The tendon would go. So he walks like tent peg. Well, he can walk 15 miles an hour, which is faster than you can run, and can catch you and kill you. But he's still just walking.
I see. Yeah.
A T-Rex can only run. His legs are bent. They're not straight like tent peg. A sauropod, on the other hand, if you go into the museum, has straight legs and they're locked together like an elephant. So he can go, well, he would go multiples of 13 to 15 miles an hour, which means he could go maybe 30 miles an hour plus, but still with straight legs.
Right.
But he weighs 60 tons. If an elephant's foot slips and falls into a ditch, his bone snaps and he dies. That's all he can do. That's it. You break a bone, elephant's leg bone, he dies. He just has to go down a couple of feet.
So
none of that engineering works.
Right. So with that in mind, then, what are your thoughts on the historical? Because this is the key question. What are your thoughts on the historical force of gravity at the Earth's surface, then?
Listen, let me give you one more example.
Okay.
Because I really have to say this. Do you remember Jurassic Park?
Yes.
The first Jurassic Park. You remember the T-Rex chasing the Jeep?
Just about.
The Jeep is coming toward us. Everybody's in it. The T-Rex is behind it, pushing bushes away. Okay. That Jeep was going 55 miles an hour, according to them. We're up to 55. Okay. The T-Rex was walking. It was walking. It goes clump, clump, clump like that, and still kept up to 55 miles an hour. Knew the guy before he died, who worked on the life-size T-Rex for the movie. Because he decided, what's his name? I can't think of his name now. Somebody will think of it. Anyway, he worked on the Jurassic Park movie and was only able to make feet and heads and stuff, but he decided to make a full-size T-Rex. Right? And sure enough, he made it. And he made it with titanium, which is pretty strong. And so he had the upper body and lower body, and they were connected, and it was one body, and he had it walking. Okay? That model, as soon as it would move, twisted so that the titanium twisted, and he could no longer use it. He had to rebuild it with one movement. Okay? So what he had to do was cut the T-Rex in half, built the upper body and built it on this big platform, 8x8 timber platform, built the upper body and built the lower body below it with the legs walking so that the thing wouldn't twist out of shape because titanium wouldn't hold it together. So, I see these things and remember, I'm an artist. I can see a T-Rex run in my head, bang, like that. I can see all these monsters go, and the relationship between the gravity and them makes sense. Just the way, you see a bear lumber along, you go, well, he's lumbering because he's so damn big and the gravity is so heavy. He'd run like a wildcat back in those days. The gravity was 1/4, if not less, than it is today. Clearly, they had giant insects. They had dragonflies with 2.5-foot wing spreads. Well, they're made out of this kind of cellophane-like material that would just snap. And they fly today because of the way the gravity and the air pressure works. Everything, there's nobody really, you can have conversations with just common folks, can you imagine this? They would say, no, it doesn't even make sense.
Right. I agree. It's pretty obvious when you think about it. And I think that certainly the flying dinosaurs and the large insects, you can make these arguments about the land dinosaurs because of their, either they didn't move very much or, they lived in swamps most of the time, as a few people.
My favorite theory now is some scientist came up with the idea that the T-Rex, when it got to be an adult, its teenage sons would go out, children would go out and get food for it.
That's a good one.
I'm trying to imagine. Wow, that's great.
That's good. That sounds like I don't know, a middle-aged man's dream life, that his kids would go out and get food once he got past 50 and he felt he couldn't walk to the restaurant or whatever.
This other thing that they say, well, what happened was as the T-Rex got bigger, it got to be kind of a scavenger, and it got to be one of those animals that would lay in wait for creatures to come by, and then it would jump out and grab them. And I'm thinking, do you know how big a T-Rex is? And what kind of a rock you'd have a T-Rex hide behind it? I'm just like, what are you saying? You people are crazy. You can't. there's a certain level of logic that you just kind of tilt your head and go, okay.
Well, I will tell you another one that I came across quite recently, and it wasn't from a scientist per se, it was from a science teacher, and he's got this web page. Maybe I'll send it to you by email later on. Just
out of it stupid, because I can't stand some of this stupid shit.
Well, it ended up being a bit stupid, but he thought that the atmosphere was basically 50 times denser, or whatever the figure should be.
Incidentally, just so you know, okay, I have a chart on my site, and I can send it to you, that shows you how much oxygen the atmosphere had and how dense the atmosphere was and what percentage of oxygen. As it turns out, back then the level of oxygen, for the most part, was the same as it is today. Just they did it recently, they figured it out, and guess what? It's all about the same. Sometimes it's up, sometimes it goes down, but it essentially stays the same.
Oh, that's interesting. I have to look at that, because we talked about that, but not really gone into a lot of detail about it. But this chap, I wrote to him, and I got quite a rude response from him when I, suggested other things. He just didn't want to know,
I know. You were talking to Mr. Wackading Hoy. I understand.
I can't remember his name, but no, I wouldn't. I don't know. He seemed okay, but then he just gave me this rude response, and I didn't really think that was very nice. Going back to the growing Earth, then, essentially what we're talking about, you would contend, or you would say the only explanation is that the mass has increased, and would I be right in saying that you would argue that the mass has increased through a process of pair production? Am I right, or?
Oh, I would say that pair production is the beginning of matter.
Right. Okay.
But the assembling of pairs into atoms would be the next step. And the next step is how do you find electrons and positrons in a place where they can exist independent of one another without joining and seeming to annihilate. Can't use the word annihilate, but they seem to disappear. So how do you keep them in a situation where that can happen, so that the next process can take place, whatever that next process is? So one of the ways you can do it is, I don't know if you know anything about the Van Allen belt.
A little bit.
The Van Allen belt, okay, the Van Allen belt has negative and positive particles on different layers. Okay, they go on independent of each other because of the layers of the electromagnetic field of the Earth. So now we're finding that, obviously we found with the Van Allen belt, that electromagnetic fields have part of their the ability to carry negative and positive particles separate from one another. Okay, now you can do that in a what do you call a collider?
Oh, right. Okay. Yeah. Yeah.
You can do that in a collider. That's how they're able to keep electrons from positrons. They use an electromagnetic field, and they have the positrons attracted to the negative portion, and the electrons attracted to the positive portion. So now you're doing in a collider the primitive version of the Van Allen belt. Well, the electromagnetic field of the Earth goes around the Earth, and at the poles goes inside the Earth, okay? And it goes inside the Earth at the outer core, okay? The electromagnetic field of the Earth travels, okay? I would insist that the outer core is not molten iron, which I think is a foolish theory, but much more logically a plasma, which molten iron potentially could be, because at that level, molten iron could easily be a gas or a plasma. And since the temperature is between 6,000 and 9,000 degrees Fahrenheit, estimated at that, could be hotter, then a plasma would make sense. Then it's possible, then since the electromagnetic field of the Earth, on the inside of the Earth, is carried in the outer core, it is reasonable to assume, I'm not saying it's a theory, it's reasonable to assume that the Van Allen belt that goes into the Earth and travels the electromagnetic field and that outer core could also have Van Allen belt layers.
Okay.
Possibly.
So
I think that it would. I don't think why it would be any different than it would be going around the Earth and inside the Earth. But
okay.
you could. Well, I don't know how. But
Okay.
if that's the case, then positrons can travel independent of electrons, especially if they're made at the core. If they're made at the core and fed into the outer core, and they can stay separate, the question then is what happens with the positrons? And this is what I say, and this unfortunately is a theory, and I don't see how I can justify it unless I can have all the instrumentation of the world to do it. But I would say this. The positron would attract those particles that the pair production is made of. Remember I said the pair production is made of these complete electromagnetic fields? Said that field was negative on the outside and positive on the inside, okay? If a positron, if either one, the electron or positron, were to attract one of those fields, it would not be the electron. Why? Because the electron, in a little field I described, is on the outside, and electron doesn't go together. A positron might attract one of those fields, in fact, probably would, but would attract it to a certain distance, and it would have to stop because there's a positron at the core. So a positron would attract the negative electron on the outside of the field, but stop. Then the question is, will it attract more? And I say it will, because this is a full positron, and this is a positron-electron, which is neutral, except it has, at a close range, negative and positive charge magnetic attraction. So I would say that if this positron can attract 5 layers geometrically created around this, that would be 1,000 layers. If you would take, because the field, electromagnetic field of the positron at the middle of this cube, that would be 1,000 particles, okay, is not going to extend out past a certain distance, then the corners would slough off, because a certain distance would not include the corners, because it wouldn't continue out there. So the corners would slough off. You lose the 10 particles. Geometrically, now you have a sound object. But you have 920 particles. Okay. If the positron can attract a cube of 1,000, knock off the corners, now you have a geometrically sound object of 920 particles. Okay. Each one of those particles has an electron and a positron, so you just double those numbers. You come out to 1,840.
Okay.
The center particle is the positron. Then you could say that it takes place of 2 particles, or one field. So it's 1,838. Then, my friend, you have a proton.
I see. Right. So can I sort of summarize that a little bit then? Again, I apologize if I get the wrong end of the stick, but what you essentially would suggest then is that we've got this process going on in the Van Allen zones where there is this way that particles can maneuver separately, particles of different charge can, travel separately without necessarily interacting. But you would say then that we've got some type of similar process going on in the outer core. I want to just pin down something that you're telling me, so check I've understood it properly. The mass of the Earth is increasing, correct? And that process you say you would propose is going on in the outer core primarily. Is that?
Yeah. Yes.
Okay.
Oh,
so then carry on for me.
No, it would be the beginning process would be the pair production that would be going on in the core. Assembly of the atoms going from positrons to protons, and then evolving. I mean, the thing that you have to remember, if you start to follow this process simply and directly, what you get is, once you get a proton, okay, that proton will then attract an electron, and you will get hydrogen. Okay, if you compress the hydrogen, you will get a neutron. If you get a neutron, and you can get neutron-proton pairs, you will go beyond hydrogen into the higher count atoms. So what happens is in the outer core, progressively outward, you get the outer core, which is the plasma outer core, accepts the new electrons and positrons, keeps them separate, allows the positrons to evolve into protons by collecting more particles, because these particles, by the way, fill the universe. These are little tiny electromagnetic fields. And the reason they fill the universe, you have to understand it, is if you took any particle of matter, okay, and guessed its size, you would have to not guess its size, you would guess the size of its electromagnetic field, which would be a fly compared to a baseball stadium. The field size is
I understand what you're saying.
Particle the size of a fly. If you take that field and wrap it inward so that it doesn't extend outward, then all you have is the fly. You have no baseball stadium. So these particles that fill the universe and make up the universe, it's what the universe is made of, okay? Until you pop them out, they don't expand out into these electromagnetic fields, so they're not there to, as far as we're concerned. All we can identify.
We don't perceive them or can't identify them, yeah.
Things that are made of half electromagnetic fields. We can't identify a whole electromagnetic field because it's compressed into itself and we can't know it because we are made of matter, and matter is made of 1/2 fields. That's what we know. We know everything that's made of 1/2 fields, which is matter. Anything that's made of whole fields, we don't know. It's the ocean in which matter exists, okay? So what happens is that this matter, this universal matter, these fields, can flow through matter like water through a sieve or like BBs through large pebbles. If you can imagine a fly in a stadium, easily they can float. So they flow through the earth. They're everywhere, okay? So they're there for pair production to happen. We can say, well, the earth is empty except for the matter. No. The earth is filled with this stuff that you can turn into matter. And when you do that, then it expands, it blossoms like a cotton boll, where you have a cotton boll and it blossoms into this magnetic field. It blossoms into matter, what we know as matter, okay? Otherwise, it's just these little tiny.
I think I get a better feeling for what you're saying now. Yeah, I can see that, I think, quite well now, and it's very interesting, sort of.
What happens now is that you, in the core, you have pair production, tremendous amount of energy going on. You get pair production. You throw these electrons and positrons into the outer core. The outer core then takes the positrons, assembles them into protons. The protons join the electrons and make neutrons. Then they start to assemble, according to where they are in the magnetic field, they start to assemble different forms of matter, gold, potassium, all this other stuff, which is then pushed outward, okay, by the heat of the earth and what we call differentiation. Differentiation takes lighter stuff and pushes it outward. Okay, that's why the continental plates are made of granitic rock, whereas the oceanic plates are made of basalt. Granitic rock is 2.7 times the weight of water. Oceanic rock, basaltic rock, is 3.3 times the weight of water. So it's much heavier. Granitic rock, volcanically and through cracks and whatever, comes up and coats the earth with granitic rock. Okay. Below it is basalt. Basalt is heavier rock, and our granitic rock comes from it. And it still keeps on coming. It's not like that the oceanic plate is just basalt. There's chunks of granitic rock coming up all the time. But it makes the outer coating because it's lighter. That's also why you get salt domes. You get two gases that come up that are lighter, but still heavier than air. And so they assemble below the surface of the earth into these salt domes. The same reason that you get geodes. The same reason you get diamonds. Diamonds are assembled particles, okay? there's a logic to the way the Earth works. The Earth isn't suddenly like an experiment, a scientific experiment. It's logical and sensible. It grows. It manufactures matter. It assembles matter. It joins the matter. It differentiates the matter and pushes it to the surface. And when it meets the level that it's comfortable at, it stops and stays there. If it's lighter, it keeps on going. That's why gas is something that people don't necessarily know. But tons and tons of air is blown off into space, okay, by the solar wind. Tons of air, of the gases. They have to be replaced. Otherwise, Earth would not have an atmosphere. So what happens is the Earth supplies its own atmosphere from the inside. The gases that come up are according to how strong the gravity is. On Mars, very little strength in the gravity, so it flies off into space. The moon replaces its tenuous atmosphere about every 2 weeks. It has a little tenuous atmosphere. The solar wind blows it away. 2 weeks later, it gets it again. Where did it come from? It comes from the inside of the moon. Okay?
I was going to ask you about that, actually, yeah, or the expansion of the moon, yeah, or growing moon.
The Earth the same way. Our air, our gases are blown off, but at the same time we replace them from the inside of the Earth, just like we replace the water, which is just two gases. This is a rejuvenating process. The Earth is the way it is because the Earth makes itself, because the sun has stopped making it. And then I didn't get into that at all yet, but the solar system is actually made by the sun, because the same process that the Earth is going through to remake itself and to add material and to add material constantly, okay, the sun does the same thing. It blows its material out into space, into its own Van Allen belts, okay, where it assembles and forms little molecules. First forms atoms and then it forms molecules. They sent spaceships out and they got this clay at the front of the spaceship, and they collect all these they're not meteorites, they're little pieces of crystal, which is assembled pieces of stuff that the sun is sending out. Then they grow and they assemble into meteorites. They assembled into meteorites. They go to the electromagnetic lines of the sun, which are mathematically spaced out, and the solar system is assembled. Then when the planets and moons get big enough, they start to do it themselves, and the solar system, the sun, makes its own solar system.
Okay, well, I can get a feel for that then. That's great. And
you've how far away from science we are. None of this is talked about.
Well, indeed, I agree. And you've mentioned a couple of things there which tie into the next couple of questions I got on my list, and I nearly got to the bottom now. And that was the origin of the oceans. So I think from what you said there, you would say that you said earlier on yourself, and we agree, and our scientists, I think, actually agree with this one. There were only shallow seas up until approximately 300 million years ago, and then at some point after that, the ocean floor, the deep ocean floor, there's nothing older than 180 million years. I got
to interrupt you. You will not believe when I tell you what scientists say, because they make so little sense that it defies logic, okay? Scientists say that while we had shallow seas on the continental plates, we also had oceans, just like we have today. Same amount, okay? Yet, on the continental plate, we had shallow seas, which were up to 800 feet deep, okay? Now, you do a little math and you have to say, well, that means that sea level was 800 feet deeper than it is today, all around the world, because the shallow seas were contiguous with the deep ocean. They continued into the deep ocean. I mean, it's not like they were isolated in a pan on the continental plate. They continued into the ocean. So ocean level then was 800 feet deeper than it is today. Call it 600, somewhere between 600 and 800. Where did all that water go? That's 1/3 of the water of the Earth gone. Or there weren't shallow seas. Of course there were shallow seas. It's all a lie. You cannot put it all together. I'm not saying it's a lie like I'm going to tell a lie. I'm saying the science doesn't work.
Doesn't stack up.
So shallow seas and have contiguous ocean, and then that ocean suddenly went somewhere.
So would you say then that the oceans were produced by the very process which you've already described?
I would go deeper than that.
Go on then.
Remember I mentioned salt domes?
Okay. Yes.
Salt domes are made, now scientists will tell you this, okay, which I can't understand why they do it, okay, but they do it because it's another theory. Salt domes are made by oceans or parts of salt water drying up over periods of time, making these salt domes that are under the ground. Okay, and we know that because there's seaweed or there's some plant material under there. No, for the most part, there's not. For the most part, in salt domes, it's just salt. Some places have some material, but essentially it's just salt. Now, these are salt domes that are approximately, I'll give you an average salt dome, 2 miles wide, 2 miles deep, 10 miles long. Can you imagine some kind of body of water that would have left salt that would be 2 miles deep, 2 miles wide, and 10 miles long? It makes no sense. It's ridiculous. It's a theory, okay? Well, if salt is made of two gases, and those two gases are made inside a very superheated earth, okay, and those gases differentiate, like they're supposed to, upward through the earth, past the molten outer core, okay, out through the vents, okay, and up in the single atoms, okay, because they're gases. That's how you become a gas. You're made out of single atoms. And float around under the earth to a level that they are the right weight for, atom-wise, atom count. Then they're essentially floating around under the earth because they're not as light as oxygen or hydrogen. Okay, they're heavier. So they float around under the earth until they find another deposit of salt. Okay, and they go and they join that deposit and add to that amount of salt. And over the millions and tens of millions and hundreds of millions of years, they become salt domes under the earth, under the surface of the earth, about the same level that oil is at.
So that this is a migration of gases, then you're saying, or gaseous material? Is that?
Sure, they join together and become salt.
Right.
Okay, safe salt. It's the only rock we eat. So they become salt domes. Now, if you've got a planet, okay, that has that's made out of granitic rock and sediments, and salt domes over a period of time are growing under the surface, you're not getting to those salt domes easily. There is one way to get to them, and that is to crack and rift the continental plate apart so deeply that it cuts into those salt domes, like in the Gulf of Mexico, which has something like 200 salt domes. Okay, cut into that, and then the salt bleeds into the water. But until that happened, the water on the continental plates in the shallow seas was probably fresh water. Okay, so now you have interesting questions. Here is fresh water on the continental plates. The continental plate cracks. The water falls into, and now the salt domes are exposed, and the salt starts bleeding into the water, and we begin 180 million years ago to have salt water on Earth. Before that, no salt water. Why did it take so long for fish to adapt to swim in the water? Because it was salt water. Interesting. Fits all the conditions of fact. Okay. Now, the point is that the water, okay, the hydrogen and the oxygen are constantly joining together on the continental plate through cracks in various places. Until you hit those salt domes, it's fresh water. And here's an interesting point. There are twice as many fish families twice as many fish families that are freshwater fish than are saltwater fish. Twice as many fish, I'm not talking about fish, I'm talking about fish families. Twice as many fish families that are freshwater fish than are saltwater fish. That means that if there were saltwater seas for billions of years, saltwater oceans, then all fish would be saltwater fish. Or certainly a majority. But it's not true. The opposite of the truth. That's when I say study enough things and start putting the facts together, it makes a very different picture.
So can I just sort of summarize a little bit of that then, and again correct me or change or add to what I'm going to say, but the origin of the oceans, you would argue then, is this same matter creation process, and what's actually happening is you're getting hydrogen and oxygen being produced by the process. There's differentiation, and then at some point that hydrogen and oxygen is coming together to form fresh water, and then where it's going to the salt domes or similar geological formations, that's when it converts into salt water. Is that a fair summary? Or?
Pretty much, yeah.
Okay, great. That's fine. That's just so long as I've got the right end of the stick. So just a couple more questions then, Neil, because I've taken up quite a bit of your time here, so thank you very much. One of the things, I don't know whether you'd agree with this, but one of the things that I'd come to understand was correct in terms of the growing Earth, or I'll use your term, growing Earth. The growing process appeared to start, or well, maybe not appeared to start, but appeared to jump in its speed 300 million years ago. Would you agree with that? And if not, why not?
Not at all. It's an exponential growth. Growth is not an event. Growth is a process. Okay. Growth increases, especially with a planet, with time. The first growth that happens with a meteorite or a small moon is called accretion. Okay. Accretion simply means that different chunks come together because the gravity that's created by the larger chunks tracks the smaller chunks, and it gets bigger and bigger and bigger. There's no processes going on inside of that except for individual atoms adding themselves to the bulk of it. And so what the individual atoms do is they kind of travel down the silicate lattices toward the center, and they do push outward, and you can see it in many, many meteorites. So they push outward. So it's a kind of growth, but it's a false growth. It's an accretionary growth that's caused by the pushing outward. But what happens is, as the core of these things, these moons, begin to heat up from the process of the accretion of the different atoms going in and pushing outward, and the friction that happens inside of it, they begin to heat up. So you start to create very simple atoms like there's a moon, it's not Enceladus, it's one of the other moons that is firing water out into space.
Europa?
Yeah. No.
Mimas, Europa, Enceladus.
No. It may be Enceladus. But it's at the southern end. It's firing water out into space, and the water freezes. So it's making lower count atoms at its core. Okay. So those gases are, some oxygen, some hydrogen, some other gases are being fired out because of the structure of the thing wants to hold them in, and they want to get out because they're gases. Gases have a tendency to move outward because the heating expands them, and they move apart and they shoot out. So then as the processes continue, higher count atoms are made and higher count atoms are made. Then you get a superheated core, and then you get a superheated undercore, which is what we have on Earth now. We don't have that on Mars because there's not enough going on, but we have a superheated undercrust, where a second level of differentiation is going on that gives us the granitic crust. So all these processes happen progressively, but the growth increases exponentially. It continues and gets more, just like the universe. I mean, one of the reasons I call this process the growing Earth, growing universe is that the same thing seems to be going on. Both Maxlow and I made a progression of the growth of the Earth. And it, sure enough, our progression matched. I mean, you could just see that line swing up.
It's an exponential growth, yes.
Yes. So as the processes increase, as the heat increases, the processes increase, more and more material is made. Remember, the more energy you have, the more pair production you make. I mean, that pair production, you can one of the things that you can find a lot of pair production in is lightning. There's a lot of, where you have lightning, you have a ton of pair production. You have almost instant annihilation or coming back together, but essentially it's the energy that creates the pair production, because you get high energy photons, bang, you start to make matter. Well, the more energy that you have, the more matter you're going to create. And that's why the sun can create its own solar system, because it's massively pair-producing material.
So, okay then, so I think I've got the gist of what you're saying. Again, correct me if I'm wrong in that. So, just taking the Earth to start off with then, you know, you would say that we had a small amount of material to begin with, which was accreted together from the material that was just, you know, round basically, and then that material began to accrete just by gravitational.
Remember, that material came from the sun.
Okay, so that material originally came from the sun.
And remember that we have this solar system accretion theory that was created or presented to us about 170 years ago by about 4 or 5 philosopher scientists who presented this theory, and we've been justifying this theory for the last 170 years. Well, that's very nice, okay, but it doesn't make any sense. It doesn't make sense that you have, you know, hydrogen, a hydrogen core, and then you have all the rocky planets, and then you have the gas planets somehow accreted out of some spinning disk. That doesn't make any sense. What makes sense is that you have a sun, okay, and your sun throws material out into its system, into its solar system. That material accumulates, and because it's not on the sun, because the sun can only make hydrogen and helium, because it's just too hot to do anything logical and sensible. To make higher count atoms, it has to strip the electrons from the hydrogen and helium, just to throw out the cores, the nucleus, into our solar system, so they can assemble in the solar system into higher count atoms at different levels of the solar system, which are then attracted to the electromagnetic lines around the sun and start to form moons and planets. So it is essentially making its own solar system. Now, my understanding is that the Earth, that our sun is probably a second level sun. So it probably started with moons. It's probably a Jupiter-like planet that grew and became a sun that already had its planets begun, because some of these planets are just too big to fit into the timeline. So its previous incarnation probably had very little in the way of planets. It just probably was a sun, you know. It started to make its own moons and the rest of it. So it's all a growing process. It's all a increasing process, and it doesn't come from outer space. It's all this, you know, assembled gases. It's assembled hydrogen, because you can't imagine a universe that has all this stuff. All it has is pair production and primitive gas. What is the most primitive gas there is? Hydrogen. Doesn't even have neutrons. It only has electrons and protons. That's it. Okay, that's the beginning of our universe, is these assembled hydrogen clumps, okay, that then process the hydrogen into helium, which then causes, it's caused to take your hydrogen atom, shove it together and make a neutron out of it, and then you can make higher count, but no more higher count atoms. So you have to fire them out into your solar system, strip them of their electrons, and let them assemble into higher count atoms, and then join in the electromagnetic field of the sun. Which leads to another question, and that question is, what is it that seems to be growing? And that is, it is not the suns that make up our universe. It is not the planets that make up our universe. Just as with the atoms of our bodies, the atoms of your body okay, are not the atoms. They are the electromagnetic fields around the atoms, okay? Those are what make your body. You have color, you have dimension, you have sense, you have logic, you have all these gifts that have been given to you. But the truth of the matter is, so little of you is the actual atoms that make up your body, and so much of you are the electromagnetic fields. That to believe that the universe is any different from that defies logic. The logic is that the universe is made of these electromagnetic fields, at the core of which we have suns and planets and the rest of that. But the fields are what we separate, just like the cells of our body and the atoms of our body. They don't compress. They don't want to compress. Fields don't like to impinge on other fields. They just move out and make room, which is what the universe is doing, which is what the cells of the body are doing.
So essentially, this is all based around the idea of a field around, or a field that's associated with an atom or basically an atom, and it's that field which is really
what matters.
That's what that's a kind of almost an oxymoron, isn't it? But it's a field that matters. Yeah, that's
Here's another thing that you have to remember. You remember I said that pair production is matter. You get an electron and you get a positron. And if you assume that progresses outward, you have to understand. And I know it's hard to understand. It really kind of goes against what we would like to believe. There's no such thing as stuff. Okay? There is no matter. Okay? Matter is energy and 1/2 electromagnetic fields. That's what matter is. It's not color. It's not solid. This isn't matter. Matter is energy plus 1/2, not a whole electromagnetic, but 1/2 electromagnetic field assembled into whatever it is that we have by the billions upon billions upon billions. Matter is not matter. There's no matter. There is no stuff. It's like calling a hurricane a thing, and then it dissolves and becomes nothing. It's no longer a thing. You are, I am. If you remove the electromagnetic field, or you slow the electromagnetic field of your body, then you'll dissipate into energy and fields that slowly stop doing. There's no stuff. So to assume that the universe isn't the same is like saying, well, then we're made out of stuff. No, we're not made out of stuff. To me, the best analogy I can think of is that fish are in the ocean. We are in the ocean of the universe, okay? Fish don't know the ocean is not nothing. In fact, the ocean around them is the same density that they are. Otherwise, they would sink. They just have a different assembly of the water that's around them into tighter molecules and looser molecules, but they essentially are exactly the same weight as the water they swim in. They're the same stuff. We are like the universe, except we are 1/2 fields and the universe is whole fields. I know that seems simplistic, but you know what? That's how the universe has to be.
I understand what you're, what you're presenting there now a lot better than I did. So yeah, it's very, very interesting, and I think I've got to the end of my questions now, really. And I think I didn't ask them all because basically you'd answered them, while you were going through the other things that you were going through. So I think you've pretty much covered all the questions that I had.
Let me try to say this to sum this up. You can't know these big questions without studying all the sciences. Mm-hmm. That each science, each specialty seems to want to pull apart its various little pieces, and nobody seems to want to put the whole thing together.
Right.
And until we start speaking the same language, until we start pulling all of these pieces together, we're not going to see the forest for the trees. All we're going to see is the mysteries that we don't understand. And the truth of the matter is that the answers have to be simpler, and they have to make sense. Once we get there, once we understand that all the sciences are involved, once we understand that we all have to speak the same language, where God knows that'll happen, we're never going to understand this stuff. So I'm presenting this as my solution, okay? And it's the only solution I can come to with all the facts. So I would prefer if anybody wants to argue with me, great, present facts. Don't present theories, suppositions, hypotheticals, facts. If we can deal with facts, we can come to the end. And I think that these are the answers, but there you go. What the what?
Okay. Okay, Neil. Well, I've very much enjoyed our conversation. I think you were going to send me some graphics. Is that still okay? Or, and what I'll do is because I didn't record, I wasn't able to get my video recorder going for Skype because I've never done that before. I don't do this a lot, as I said. I only do it from time to time. But I have got all the audio down now, so I'm quite happy to insert any graphics.
Okay.
And
I've got graphics on the assembly of atoms. I've got the
great
positron thing. I've got all that for you.
Okay, well, I'll look on your website as well, and then I'll send you an email, and maybe I'll just say a few closing words.
There's a lot.
Sorry.
There's a lot there. I would like to go and collect that stuff if I were you. I might.
Okay.
Forget.
Yeah, I will do. So I think, Neil, again, thank you very much for taking time and going through all of this. I found it very, very interesting, and I think that other people, hopefully when I make this into a video and I post it, will also find it very, very interesting too. And obviously I think we're both going to keep looking at this and refining it. And again, thank you very much.
Okay. See ya.
You take care.
Bye-bye.
Thank you.